parallel pumps, one's redundant, it's 200 gallons a minute. We have two air handlers at 100 gallons a minute apiece. So, a 4-inch pipe out here, 3-inch pipe here. The way we size this pipe, there are all kinds of manufacturers and tables, but assuming you got standard steel pipe, normally pipe is sized, kind of look at velocity, maximum 8 to 10 feet per second for erosion, and noise probably 6 feet per second for the least amount of noise. So if you're above the ceiling, you know, somebody might size pipe on 6 feet per second. If you're in a mechanical room or underground, you might size it for 8 to 10 feet per second. When I worked on these kind of jobs, I always worked in areas that were always going to add on. So I was very conservative. I was always down around this 6 feet per second, knowing that I could go up to 8, 10 feet per second. So if I just look at some tables and piping, at 200 gallons a minute, the velocity in a standard steel pipe is about 5 feet per second. So I'm good there. And the pressure drop of a not necessarily a clean pipe, but a pipe that's been in operation for some time is so 4-inch, 200 gallons per minute, 5 feet per second, and 5.1 feet pressure drop per 100 feet of pipe. So now I can start adding things up and start looking at how my pump is affected. And a chiller, I kind of, I get a selection on a chiller, and this particular chiller at 200 gallons a minute has a, say a 5 PSI pressure drop. My coils from my air handling unit are going to given to me, and they're probably 7 PSI. I'll make that a little less. Say 4 PSI pressure drop in each one. Okay. So I know my chiller, I know my air handling units, and I got this piping system that's running out through the building. And from here to here, it's 4-inch. And it's 200 gallons a minute. So I start looking at my components, okay? So I've got a 4-inch gate valve, 4-inch check valve, 4-inch strainer, 4-inch air separator up here, the purpose of that is to remove the air in the line, go through an automatic air vent. And that spits and bleeds to a drain. I got my expansion tank. Of course, it's not in the line, so it doesn't affect the pressure drop. And I got balancing valves. Could be any kind of balancing valve. We'll just say globe valves. Go back here, 4-inch globe valve. Okay. Peach plugs, thermometers, they're not in the line. The T is so small, it doesn't affect anything. So I covered everything. I got strainers, I got check valves. The reason for that check valve again, these are parallel pumps that could operate at the same time. They could operate independently, but even if this pump is off, that pump is on, I don't have a check valve right here, and the water, some of the water is just going to go just like that. The reason for that check valve is to prevent backwards flow when you have parallel pumps. The strainer got a screen in it, and it protects any large trash in the pipe and getting to the pump and getting back to the coils. So then I've got, over here, I've got 2-inch gate valves and a 2-inch globe valve for balancing. And I didn't draw in my control valve. Okay. Then I've got a control valve. It's going to have pressure drop. And then I've got a coil. And I've got, I'm going to keep a separate tab for pressure drops that I know. I've got a chiller, I've got coils, I've got control valves. Okay, mostly, now I know that I specified this control valve with a certain pressure drop so that the controls contractor can select the valve. And I want that to be 3 PSIG. I want the control man to select a valve that has a 3 PSIG drop. That way I know that the valve is going to be adequately sized and have enough pressure drop to work correctly. Get too large a valve, the valve cracks open, you can't control the flow. Too small a valve, you're not going to get enough flow through the control valve. But a 3 PSI valve will give me approximately a good selection on a valve that I know would work. So I know I have known pressure drops, chillers, coils, and valves. Everything else I got to figure it out. So I know that this 4-inch pipe is at 5 feet per second. I know it's at 5.1 feet per 100 feet of pressure drop. So I've got 4-inch pipe, and I've got 4-inch L's, 4-inch T's. So I kind of got everything in my system that I know that I've got. And again, you can go to various manufacturers and charts. And I know that a gate valve
Steve,
yeah.
will you be affected by a bunch of 90s and 45s in that system?
Well, that's what we're going to do. That's what we're going to give you an idea of how this compares to these things.
Okay.
I'm going to tell you. So let's just say that I know that this is a 2D drawing, but I know I've got 1, 2, or I could take the worst case, I could go across T here to the elbow, across T there, that's going to have more pressure drop than that straight through T. And straight through T is not going to have any pressure drop at all. So I've got 1, 2 T's, and through experience, I might say that this is my design leg, assuming that all this piping is the same. Through experience, I might know that that cross T pressure drop is higher than that straight run of pipe and elbow, assuming that the air handling units are close together. But let's just say they're not. So we'll know the differences. I got a straight through T. We're going to say that all this piping from here, 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 we're just going to say it's 300 feet. Okay? And I've got 2 T's. 2 T's. I've got, who knows how many L's, just come up with a number, let's just say 20 elbows in the pipe. And I'll show you how much pressure drop each elbow is. And I got globe valves, I got balancing valves on each pump, but these pumps are in parallel, one's redundant, so I really only have flow through one pump. I'm only going to add up one balancing valve right there. Air separator, I've got one of those. One Y strainer here in front of the pump, protect my piping system. Got one of those. Got one check valve on the pump. And I've got 1, 2, 3, 4 gate valves. Okay, so I add all these things up, and what it's going to do is give me the equivalent feet of pipe that I've got. I've got 300 feet of pipe, but all these things have pressure drop, and I'm going to measure these in equivalent feet of pipe. For instance, a gate valve has, it's got a straight edge. You can take a piece of paper there. The gate valve, let's see, gate valve. Yeah. 50.
How often did you run across when you designed the system and then the contractor was out there and it turned into a nightmare? And you
Depends on how well you designed the system.
Okay.
You know, if you knew what was going on and if you designed it, if you took into account all the ductwork, the conduit, the cable trays, and you laid out your piping system with some experience and knowledge, then you got it very close. But yeah, there's always going to be some additional elbows, and I'll tell you how I took care of that.
Okay.
So a 4-inch elbow, 4-inch straight open gate valve only has 2 feet of equivalent pipe. That's all it's at. A globe valve, fully open, has 120 feet. 120 feet of equivalent pipe.
What's the makeup of a globe valve? How does,
The globe valve is like our standard control valve is a globe valve.
why, oh, I see, just because it's not fully open line?
See if I can show you a picture.
I guess my question is, how come that has so much,
The way the valve is made up inside, a gate valve, if you look at a gate valve, bonnet, it has a disc in it that actually rises up out of the string. I got a thread here, gears in here, this is the disc that actually comes down. I may have an opening in the pipe like this, and that disc comes down, it's closed. So there actually is very little interference in the pipe string, right? Well, a globe valve or some kind of balancing valve is more constructed where the water flow comes in here and it's got a disc that sits right here that rises. So the water has to come in, has to go through that orifice, and come back around.
I got you.
And it's designed to, it can, based on the position of that disc, can actually do some balancing. There are other types, I mean, ball valves make very good balancing valves at very low pressure drop.
Why would you want to use that disc valve?
Most people don't use globe valves anymore I'm kind of using it as an example to show you the differences.
Oh, okay.
Now, a ball valve could be used as a balancing valve. Needle valves can be used as balancing valves. Several manufacturers make something called like a circuit setter. I don't know the actual makeup of that circuit setter, but it's going to be the newer technology that's going to have is going to be somewhere between these. But a balancing valve will have a high pressure drop.
You understand about it?
Yep.
Okay.
Now, the balancing valve is what I want to use here to set the flows through the coils. It's the initial startup of the job. Now, in a variable volume application, we talked about having very critically sized control valves and eliminating that. Because that's energy dollars. That's pressure drop, that's costing me money to operate. So in a variable volume application, I would argue the point that we don't need this, because I'm going to furnish a good enough valve that under control will balance the entire system.
What does a triple duty valve do?
Triple duty valve is a combination strainer, balancing valve, and check valve. And it has even a higher pressure drop than a globe valve. But, I mean, once you combine the strainer and the check valve and the balancing valve, it's these three valves in one valve. And it can also, some people actually use it as the shutoff valve. That's a mistake, because how do I work on it if I don't put a valve in front of it? Actually, it's not a strainer. It's the gate valve, it's the globe valve, and the check valve. It's not a strainer. So in some cases, it would go right here. These three valves would be your triple duty valve. And a lot of people take it at its word, and that's what they put right here with no isolation valve, and it requires a lot of maintenance. Get stuck.
I just run into three of them.
It's very high pressure drop. Okay. Check valve, 4-inch check valve, and there's different types of check valves. There's swing check valves, there's butterfly spring-operated check valves, which actually have a little bit less pressure drop than just the swing, because that spring has very little tension. Swing check valve is about 28 feet. 28 feet of equivalent 4-inch pipe. Strainer. Pipe pattern strainers, 2 4-inch. And I'm just going to use a line size strainer, even though I don't have to use a line size strainer, but if you use a bigger one, it costs money. If you use a smaller one, it costs energy. So a 4-inch line size strainer at 200 gallons a minute is about an actual pressure drop of about 0.6 psi. So I'm going to move that over to here. Strainer, 0.6 psi.
That's ideal condition, so that's a clean strainer.
It's a clean strainer. But you should, I know that I said this is 3 psi. Coils were 3 psi. Did I say that? Yeah. No?
Four.
PSI. Pounds per square inch. Chiller was 5. PSI is actual measurement. PSI-G includes atmospheric pressure. How do I spell atmospheric? So PSI-G is that number plus 14.7 PSI. That's atmospheric pressure at this elevation, about 200 feet elevation. So when you're talking PSIG, when you're looking at a gauge, it actually includes atmospheric pressure. These are actual pressure drops that we're dealing on an individual basis, so we don't need the gauge pressure. Okay, strainer we moved out. And an air separator, not very much, we'll look at it anyway. I'll get on in a minute. 4-inch. It's the actual pressure. It's about 8 feet. So I know what the actual pressure drop of that is at my known flow. It was 0.8 feet. Actual pressure drop, not per 100 feet, but actual pressure. And I'll show you how to convert feet to PSI. So in our pipe, we said was 5.1 feet per 100 feet. So what's 3 times 5.1? 16 point, or 15.3? Just say 15 feet. So now, you gotta start thinking, I got 300 feet of pipe, and the pressure drop of that 300 feet of pipe is 15 feet. One globe valve is 120 feet. One check valve is 28 feet. One check valve is greater than my pressure loss from here all the way to here. And let's look at elbows. Now, what I could do, I said, well, I might save some money. I might go to a 3-inch pipe because my pipe has very little pressure drop. But what happens, all these things start going up too. The 3-inch check valve, 3-inch strainer. And so I'm really sizing that pipe on future capacity, and so that that CEO or that guy in the office that has that 4-inch pipe run across the ceiling, which is a bad idea anyway, doesn't call and say, I hear something.
Question, he also says that pipe for like a few years down the road when the pipe starts getting kind of filled in.
Well, that I can size the pipe on the C factors of C100 or C150. C150 is clean, brand new pipe.
Okay.
The number I put up here is about a C130. C150 being at the end of its life.
Okay.
It's got very extremely rough surfaces. So actually what I've done, what the Cameron book tells me, is a very clean pipe. To give you an example, 4-inch pipe, brand new, is 2.25 feet per 100 at 200 gallons a minute. At C130, which is medium roughness, it's 5 feet per 100. So I'm actually double my, because I'm conservative, I've doubled the amount of loss on the pipe.
So that means that it's gonna be quieter when it's new.
Well, roughness doesn't add too much velocity. Velocity is going to be your, tell you how quiet the pipe is. Unless you get something stuck in there like a glove or, which happens.
No.
Yeah. He welds them one day and puts his glove in the end of the pipe, and you show up the next day. Just put the pipe in the end.
Find some 4x4, huh?
2x4s.
Yeah. Elbows, we're talking about elbows. And Mark, Lisa, and use it. So I'm going to use standard elbow, not a long sweep elbow, but a standard elbow. 4-inch pipe is 12 feet. So I got 20 of them, 20 times 12. 40?
240.
240. So all my elbows in that pipe mounted to 240 feet of pipe, equivalent length of pipe. Each elbow is equivalent to 12 feet of pipe, stick of pipe. So not too big a deal, but some amount of deal. And the last one is a T. and we said we were gonna figure a side flow T. Inch is 20 feet. So that's 40 feet pipe. Give you an example, the straight through T is 3 feet. This is a cross flow T, 20 feet equivalent pipe. Straight through T is 3 feet equivalent pipe.
Is that because some of it has a tendency to migrate down like that?
No, it's just the friction loss that it takes to turn that elbow in that pipe,
Okay.
or in that T. So I've got all my piping, now I need to do my 2-inch gate valve. Each gate valve is a little over 1 foot. How many did I have? 2 times 1 is 2 feet equivalent pipe. A balancing valve is 3-inch pipe. Balancing valve is 85 feet. And I've got 1, that's 85 feet equivalent pipe. And a 3-inch pipe, 100 gallons a minute, is 4.5 feet. .5 feet per 100. And let's just say we got 100 feet of pipe, so that's 4.5 feet. Say if this is 100 feet, this was 300 feet. Okay, so now I got all this added up. So what's this add up to, John?
I added up everything.
These numbers right here?
Just just those numbers?
Yeah, 405.
Okay.
Pretty close. Pretty close. Or maybe it's not 440.
445.
445 feet. Okay, so I got a total of 445 feet. 4-inch pipe. 445 divided by 100 times 5.1.
22.7.
23 feet of pipe. Okay, here I've got 87, 92, 96, 97 feet. What that adds up to be? This right here,
91.5.
90.5?
91.5.
92 feet divided by 100 times 4.5. 92 feet per 100, pressure drop per 100 feet, so I divide 92 by 100.
4.1.
4.1. 3-inch pipe is 4 feet. Okay, so I get all these units in the same units. So 1 PSI is equal to 2.3 feet. So times 2.3 times 2.3 times 2.3. So I got 1 foot out here,
11.5.
and 11, round off to 12. 4 times 2.3 is 10.
9.2.
3 times 2.3 is 7.
Yeah.
And 0.7 times 2.3,
1.3.
123.4. Okay, what's that add up to?
$57.
57 feet of pressure drop. What's that divided by 2.3?
24.7.
Or 25 PSI drop in our piping system. So let's just look at the chiller and the coils and the strainer. The strainer wasn't very much, but 21, what's 21 divided by 57?
0.368.
40% of my pressure drop. So what happens when that coil, that strainer, or I mean that chiller gets dirt in it? Yeah. Pressure drop is comparable to, let's see, pressure drop 1 divided by pressure drop 2 is equal to Q or GPM 1 divided by GPM 2 squared. So as this number goes down, my flow goes down as it's squared. So if my pressure drop doubles, my flow goes down to 25%. So you can see, kind of the point I'm making is piping, yes, is critical, but it's only, we take all the components out. Piping was 27, was about 50% of my pressure loss for the entire system. And this is pretty standard. I mean, these rules of thumb are going to be, unless I've just got a huge building or a campus where I'm running thousands of feet of pipe. So you can see elbows. You know, what I would do, you know, now as a designer, I'm just going to put a safety factor on that. And if, you know, if I don't have a good set of drawings, the safety factor's higher. I've got a good set of drawings, got to have a good set, and the safety factor's lower. And then, you know, like I said the other day, there's some people that take things out to 2 or 3 digits, you know, past the decimal. That's kind of ridiculous. But so now I got a pump. I got to select these pumps. I don't have any pump curves because I don't have access to them. But pump curve looks like we got head and flow, and you've got impellers inside each pump that operate something like this. But then I'll have little circles in here that show me efficiency. So right here is 200 gallons a minute, and right here is, let's say, just 60 feet ahead. So if I had this particular pump curve, and I plotted these lines, so it intersects right there on, let's say this is a 4-inch impeller, and this is a 4.5-inch impeller, and that's a 5-inch impeller. And right in the eye of the best efficiency, well, this is something like 75 and 70 and 65% efficiency lines that show up on the curve. So I've got a pretty damn good selection here. And I'm right in the middle of the curve. I'm right in the eye of the efficiency. So that would be, if I had a pump curve, that's probably something like a 2-inch pump. One thing we didn't add in here is probably reducers right here. They'll have some effect on pressure drop, but negligible. So there's my pump.
Question, why would you put the reducers in there?
Well, probably for a 200 gallon a minute pump, it's probably a 2-inch connection or 2.5-inch connection. I got a 4-inch line. I mean, I don't know that for a fact, but I know that a 4-inch pump will probably do 500 or 600 gallons a minute.
Should be kind of a control turtle thing.
Yeah, I mean, it's just whatever size the pump ends up being, 2, 2.5.
Oh, okay, I see, because you have a pump.
It's just the connection size.
Okay, I got you.
Yeah. Now, this is a closed piping system, meaning that if I'm on the ground floor, I got to pump up to the top of the building, 10-story building, and I come right back down. It's a closed piping system. I got just as much head going up as I do going down, so I don't add any H to my pump. Now let's compare that to a coolant tower. Same piping system. I mean, this could be the chiller, this could be the coolant tower. So I'm pumping out of the coolant tower into the chiller, back to the system. But a coolant tower generally is an open piping system. So what's different right here at the cooling tower? I've got the same similar flows, similar type fittings, similar chiller barrel, so it's going to have, you know, very similar calculation. But now I got this coolant tower sitting out here. There's my tube pump. There's my return line coming out here. Usually connecting something like that right there, going down through the internal basins, hot water distribution, across the field, or the lip drift eliminators, down through the field, eventually drips down to the basin. Well, this is open, right? So now I've got to compensate for lifting that pipe up. There's H, that right there. So when I have this calculate my pressure loss through my pipe and fittings, this is an actual lift. Then I got to lift that water up because it's open inside here, so that coolant tower is 15 feet tall. I have to actually add 15 feet right here to come up with 72 feet. I'm not saying that the pressure drop's the same on the chiller side, I mean on the tower side, because there's going to be a lot less pipe.
Do you take any consideration of your balancing valves on top of your tower?
Yeah, you might have some more balancing valves here. They would just figure into your piping loss. Same calculation we went through. Got the valves at the chiller, valves at the coolant tower. But then, since I've got an open coolant tower, I had to figure this H in right here, the lift. So whatever my pipe loss and fitting loss I have, add the actual lift for a coolant tower pump. Okay. Any questions?
Yes. How would you determine what your pressure should be when you pipe in there?
I'm sorry, say it again.
Well, like on your suction and discharge
Uh-huh.
of that system, how would you determine what, say, if you just walk up and you start checking your peak flow, how would you determine what kind of pressure you should have on that system?
Well, it's kind of hard to do. I mean, I could take a pressure drop.
Well, I mean,
Here.
like whenever I go up to a building that's existing,
Uh-huh.
and I just start logging things in and I'm checking my pressures, it's kind of hard to tell.
Kind of hard to tell.
Okay.
I mean, you know that how much static pressure you've got to have because of the height of the building. So you know what your relief valve, your makeup valve ought to be set at. Then you really have to find out these values right here. And really what you're looking at as far as diagnosing the piping system is actually taking that pressure drop right there. And if I know that it's 5 pounds at 200 JPM, and I measure 8 pounds, and I know that this is going to be a lot less. If I measure 4 pounds, I know that's going to be a lot more. On a clean chiller, I should be able to determine what my system flow is just by coming to this point and measuring the pressure drop. And that's just, if I have these two known data, then I can measure that. So I know that my P1 is 5 and 200 GPM, but I measure 3 pounds. So what's 5 divided by 3 squared?
2 point something.
Five divided by 3 squared, 0.5.
It is 0.5?
0.55.
Is 5 squared, divided by 3 squared?
No, it's 5 divided by 3 squared.
Oh, okay, I got
Let's
it.
say it's 2.5, that's a, or it's 2, so that'd be 4. Yeah. Yeah, what was 5 divided by 3?
1.66,
And square that number. 1.66 times 1.66.
2.76.
0.76. Okay. So if I don't think that's right.
It's 5 divided by 3, right?
Yeah, right, okay. So my flow is 2.76 times 200, just by dropping that to 3 pounds. If I raised it to 6 pounds, what's 6 divided by 5 squared?
1.44.
1.44. So that's about 150 gallons a minute, something like that. What's
1.44 times 200?
no, no, no.
Oh.
No. What's the reciprocal of that number right there? You know, that on your calculator? Okay. Oh, no, I take that back. What's 5 divided by 6? That's right. No, that's down here. That's right. It was right the first time. So again, all I need to know is what the original conditions were and then measure the pressure drop. And I can calculate what the flow is, what your flow should be. But I don't know how much pipe, I don't know all the fittings, I can't predict the system loss without actually going in and calculating. I mean, I can know what the system loss is, because if I can measure the flow here, I can measure the head here and compare it to what is originally designed. For instance, we're designing our pump at 60 feet ahead, 60 feet at 200 gallons per minute. But if I go out here and measure this and I determine that my flow is 250 gallons a minute and my pressure drop, I should actually be able to predict, again, pressure drop flow changes as the square of the pressure drop. I can predict what my head should be, but I can go out here and actually measure it. And then I can work backwards again to know what the actual flow was, or actual head was. It's just, you can do what you're saying, but you got to measure the head here, measure the flow here, and then you can see what your actual system losses are installed compared to what was originally designed. Okay.
Are those values pretty representative regardless of pipe size? The apprentice, the ratio is going to be about the same if we're dealing with a 2-inch system or a 12-inch
Yeah.
system?
Most HVAC systems operate in the 60 to 100 feet ahead range. But comparison to fittings versus pipe, yeah. And that's the point I was trying to make, is my pipe and elbows and T's. A lot of people get real concerned about adding an elbow. It's insignificant, but these big devices are here, these coils, pressure drop, strainers, and check valves. Okay. And then the different, and a boiler system would operate just the same. I mean, the boiler might have very low pressure drop here, but pipe calculations and that type of thing are. So since boilers have very low pressure drop, If the chill water system normally operates at 60 to 100 feet, then you'll find blower systems operating at 40 to 80 feet. Okay? Is there anything else in this that you'd want to delve into deeper? Any special component to talk about tomorrow or Thursday? Okay. We knocked this out in a day. I thought we'd take 2 days. So I'll have to do some thinking about what we're going to do Thursday and then getting to the point where we might start delving into the controls side of this thing and go back through the things that we've already looked at: air handling units, chillers, coils, sequence of operations.
Do you have pump curves?
I can get some pump curves. We don't sell pumps, so I don't have access to them. I get them on the internet. Yeah. Show you some actual pump curves.
I think that would be beneficial.
Okay. We'll just take this information and go through the selection of a pump. We'll do one for chiller, one for cooling tower. We'll see the net positive suction head we talked about the other day. How to make sure that your pump won't operate, won't cavitate when it's operating on the cooling tower side. And we'll talk about elevation differences and go through the calculation process of calculating that positive suction head. It's pretty simple once you've done it once and see. Go through the calculation, unless you just got a tremendous length of pipe, again, any elevation, the cooling tower is above the pump will work. Again, because you've got, you calculate this gauge pressure too. So you start out with 14.7 pounds, even at the same elevation, and you start subtracting your little pipe losses. So whatever your pipe losses are, is just how much you set that cooling tower above the pump. We'll talk about that Thursday.
How often do you see a condenser water pump running in a vacuum?
20% of the time.
Okay. I know Victor buildings does.
Yeah. You've got not big enough pipe, cooling tower's not, above the pump enough. Operating in a vacuum is not that necessarily a bad deal if you compare it to, and I'll show you on the net positive suction curve of your pump. So operating at a few feet of vacuum, it may not necessarily be that bad a deal. Operating at 10, 20 feet of vacuum, a pump's gonna make a lot of noise.
It's a pain to get burned.
But we selected the closed loop system at, something less than 6 feet per 100, and maybe a reasonable pressure drop per 100 feet of pipe. In a cooling tower suction, when we go through this net positive suction head calculation, you'll see you don't want any pressure loss. So that pump suction from the cooling tower may actually be larger than your discharge pipe, because I didn't want any pressure loss in that pipe. So you might see an 8-inch suction and a 6-inch discharge on a pump for a cooling tower on occasion. Not very often, but depends on, again, how far is that cooling tower away from the pump